In this video, we are going to discuss database normalization. Normalization is the process of organizing data in your database so that the data is easy to use and easy to maintain. We primarily do this by minimizing redundancy. Now, when you have multiple copies of same data, which is duplicate data, then it can cause multitude of issues. For example, if address information is stored in many different places, and when I change my address, I have to make sure all these copies are updated. Otherwise, it can cause data inconsistency issues. And we also want to ensure data integrity. For example, if a new student enrolls in a program and signs up for a course, and if somebody goes and deletes the course, then all of a sudden you have a situation where a student has enrolled in a course and the course no longer exists. So we want to avoid those kind of issues. And to accomplish all this, we go through the process of normalization. Let's look at one example. Let's say we are provided with a spreadsheet with student enrollment information, and we are tasked with developing a database to store this information. So how do we go about it? So this is where the normalization process comes into picture. The normalization process is broken down into multiple simple steps. So these are called as normal forms, first normal form, second normal form, and so forth. And in each one of these phases, we are going to focus on specific aspects of database design. So for example, when you look at first normal form, we want to make sure the table design itself is meeting some basic criteria. Like how do we organize the rows and columns and so forth. Now, once that is taken care of, in the second normal form, we are going to look for redundancies caused due to composite primary keys. The choice of primary key that we make has an impact on how much duplication happens in the data. We are going to look for specific patterns where the primary key itself can cause duplication. And avoid that. And in the third normal form, we are going to look at redundancies caused due to non-primary keys, rest of the columns. As we go through our exercise with student enrollment data, we will perform some optimization in each one of these stages. So let's work on first normal form now. In first normal form, we need to ensure all our columns have atomic values. So what this means is that the value that is stored in each column should be indivisible and of single data type. One extreme case is, for example, you can store all this information in a single column, collapse them into a single column, but that kind of a structure will not be very useful. So instead, we had to separate the information such that each column has one piece of information. So let's walk through this. So let's look at our sample data set and see which one of these columns have atomic values and so forth. Now, if you look at student ID column, each student has a unique ID, S01, S02, and so forth. Now, these are atomic by nature because we cannot divide a student identifier. So this particular column meets the requirement. Now, if you look at the name column, looks like we are storing only the first names here. So in case if you have a last name, you can separate that out into a separate last name column. So for now, name column also looks okay because we are going to store only the first names. Now, if you look at the address column, you see the complete address stored in a single field. So address is typically made up of street, city, and state, and zip code or postal code. Now, if you store everything into a single field, it can make your queries more complex. So for example, let's say you want to find all students who are from a particular state who are enrolled in your program. Now, you have to parse this address field and extract state information and then do a filtering. Looks like too much of work. So instead, if you structure this data a little bit differently, it will make the query so much easier. So currently this is not atomic. So we need to come and take care of it. And similarly, if you look at the course column, so this column has a list of courses the student has enrolled in. And you have an array or list of values here. Now this is also not atomic because you have many different courses in a single column. Now this can also cause some issues because let's say you want to find all the students who are enrolled in English. Now all of a sudden you have to go through this list of values and look for a match for the course that you are interested in. So you have one student enrolled in English, another student enrolled in English here, and so forth. So writing queries that work with a list of values can be more difficult and unnecessarily complicate things. Now, there could also be other issues because, for example, let's say a student withdraws from a particular course. Let's say Alice withdraws from chemistry. Now, all of a sudden, we have to walk the list and remove an item from the list and then update the course column. So the course column is also not meeting this atomic value requirement. So we need to come back and take a look at this. Now let's look at other criteria. So the next criteria is that all the columns should have a unique column names. So in fact, we are meeting that requirement here. All the columns are clearly marked. So we are good here. Student ID, name, address, and course. And then the order of rows do not matter. So what this is saying is that the rows should be independent and they should not depend on each other. So I can pull this information in any order I want and without losing the meaning of data. So that's what that requirement calls for. So in this example, we have one row per student. So I think we are good here. And then there's also a requirement that we should avoid identical columns. So these 4 columns store 4 different pieces of information. So we are also meeting this requirement currently. So we in fact met 3 out of 4 requirements. So let's see how we can handle this atomic value requirement. In case of an address column, all we have to do is break it into individual columns, separate columns. So the structure would look something like this. So address field was separated into street, city, state, and postal code. Now with this structure, if you want to do a lookup on students who are from a particular state, all you have to do is come and write your query that filters based on the state column. So much easier now. Similarly, you can do search by postal code or city or by name and so forth. So the solution for breaking that address was relatively straightforward. We just separate into multiple columns and store a specific piece of information in each of these columns. Now, what do we do with the course column? Can we apply the same concept for the course column? Can we create multiple columns for the courses? Let's see how that solution would look like. So in this example, we created 3 course columns, course 1, 2, and 3. And then we added 1 course in each of these columns. Now, is this a good solution? What do you think? Now, just by looking at it, it does indeed appear to be a good solution because we are able to store 1 course in each of these columns and we are meeting the atomic value property. However, if you look at these first normal form rules, the 4th rule says avoid identical columns. So what this is telling you is that don't create multiple copies of columns that store same or similar information. Why so? So the course column is in fact violating this requirement because all these columns are storing similar pieces of information. Basically, they are storing course information. Now, let's say I want to find all the students who are enrolled in English. Now, what do? I have to look for course 1 column If anyone is enrolled in English, there is one student who is enrolled in English here. And I had to look for course 2 column, and we have one entry here. And we had to also look at course 3 and so forth. Now, all of a sudden, a simple query to look for students enrolled in a particular course requires comparison against these 3 columns. Now, another issue is that obviously a student cannot graduate by just signing up for these 3 courses. They may have to enroll in several courses. So how many columns are we going to add now? Are we going to add 10 more columns or 20 more columns or maybe even 100 more columns and so forth? So that will make your queries even more complex. Now you had to, if you're looking for students enrolled in a particular course, you have to compare values across all these 100 columns. So clearly it's not ideal. Now another issue you will run into is that if a student withdraws from a particular course, now let's say Alice withdraws from chemistry. So we had to go and look for all these columns and see where chemistry is there and then remove it. Now all of a sudden you have empty spaces in between. So your application logic will become more complex now. Now when Alice enrolls in a new course, can we put that course in this course 2 column or put it in course 4 and so forth? So this is not ideal. This is not recommended because it also violates first normal form. So instead what we are going to do is we are going to create a single course column, and we're going to store only one course in the as value for each row. In this example, Alice is enrolled in 3 courses. So that means we need to put 3 rows, 1 row for each course. Now this structure meets requirements for first normal form because we have atomic columns. Each column stores one piece of information. So including course column, you have only one course information in each row. And all the column names are unique. And then we also avoid similar columns. And then there was one more rule, which was order of rows do not matter. So here also order of rows do not matter because we can pull information in any order we desire. With this design, we are indeed conforming to first normal form. However, as you can see, we are duplicating a lot of details. So data duplication is not good. So let's see how we can handle that in the second normal form. So we are in a second stage of normalization, second normal form, because we already completed the first normal form. So let's see the rules for second normal form. So in order to go into the second phase, we have to make sure we already comply with the first normal form, which we already did. And then we also need to have a primary key to uniquely identify a row. Now a primary key is a collection of one or more columns. In fact, it should be a minimal set of columns that can uniquely identify a row. So we need to have a primary key. And then more interestingly, we are going to look at duplication caused by composite primary keys. A composite primary key is one where you have more than one column that is part of the primary key. So when you have a composite primary key, it's possible that some of your data might be duplicated. Now, before we go into primary key discussion and some of the concepts around it, if you look at this data, what is the issue with duplication? Now, for example, let's say Alice moves to a different address. Now, Alice's address got updated for one of the records, but the other 2 records are still showing the old address. Now, we don't know which address is correct because now you have a data inconsistency issue. So we want to avoid these kind of issues. So in general, duplication can cause these kind of problems. So let's see how we can resolve it. Now, before we go into defining primary keys and avoiding duplicates, let's look at the concept called functional dependencies. Functional dependencies is a term that is used to highlight the fact that some of these columns might be related to each other. Here we have complete address Address is typically organized as a hierarchy. And so, for example, from postal code, we can reliably find the state. Similarly, from postal code, we can also find the city. When you have a relationship like this, where you have columns, from one column you can figure out what the other column value is, these kind of relationships are called as functional dependency. So here we state that state column is functionally dependent on postal code. Similarly, city is functionally dependent on postal code. So why is this relationship important? Because once you figure out how these columns are related, conceptually we can avoid storing all this information. So for example, if you just store the postal code alone, we don't really need to store city and state information here and duplicate it, right? So every time a postal code repeats, the same state information and city information is getting repeated. So instead, what we can do is we can have a lookup table that has postal code to state and city mapping. And then we can use that lookup table to figure out what the city and state are. So when you identify these kind of dependencies, you can optimize your database that way. So that is the basic idea behind functional dependency. We are seeing which columns are dependent on which columns and so forth. Now let's take a look at student ID. So we have student ID here because each student has a unique student ID. So what this also means is that whenever student ID appears in your table, the name, complete address of the students are also getting repeated, right? So from a student ID, we can uniquely identify a student's name and their complete address. So we can state that name and complete address are functionally dependent on student ID. Now, can the reverse be true? So for example, can we find from name, can we find the student ID and complete address? Is that possible? Now, if you look at this data set, each student has a unique name, so it might work. However, it's possible that many students have identical names. There could be 2 Alices, 2 Bobs, and so forth. So in that case, we cannot really uniquely identify a particular student just with name. So here, name is not a reliable way to uniquely identify a particular student. Whereas with student ID, because whenever a student joins a program, they're assigned a unique ID. Student ID is a more concrete and reliable way to uniquely identify a student. So this is a valid functional dependency. So what this also means is that I don't have to repeat all this information in this table. All I have to do is keep track of student ID and then have a lookup table somewhere else that has student ID to name and address mapping. So that way we can avoid all this duplication. So that is the basic idea behind how we approach redundancy. So with this information, let's see if we can figure out a primary key for this table. So with student ID, we are able to figure out the rest of these columns. But student ID alone is not enough to uniquely identify each row. So with the primary key, we need to be able to identify each row uniquely. So the only other piece of information that we need is the course information. Because each student can enroll in many courses, and every time they enroll in a course, we add a new row in this table. So a combination of student ID plus course, when you combine these 2 columns together, we can uniquely identify each row. So for example, S01 and math, and with these 2 combination, we can identify each row uniquely. So for example, S02 and English, there is only one row with that values, student ID S02 and English. So this is a good candidate key for primary key. So usual convention is to underline the primary key columns. So we have student ID and course together because those two are primary key columns. So we keep them together. And with the primary key identified, let's evaluate the conditions for second normal form. So our table is already in first normal form, and we also have a primary key now. Now the third condition says avoid duplication of data caused by composite primary keys. Since our primary key is made up of two columns, it is a composite primary key. So what this means is that the subset of columns, so in this case, if you take student ID alone, student ID is repeating, and that is causing duplication of data for Alice, Bob, and so forth. So this is an example of duplication caused by primary key itself, composite primary key. Because part of the primary key is repeating, and that is causing duplication of data. So this is violating second normal form rules. So whenever we run into these kind of issues, we break this large table into smaller tables, like a lookup table, and then establish relationships between them. So let's see how that solution would look like. So we're going to create a student table that has student ID and student's complete address information. So each student is appearing only once in this table. So we're going to store the address and student name, everything in only one place and only once. And we have a student course table. So this table now keeps track of student and what courses they are enrolled in. So here we have student ID repeating multiple times, and for every course they enroll in, we add the student ID and then the course information. So Alice enrolled in 3 courses, so 3 times and 3 different courses. However, now if you look at it, our primary key is still student ID and course, but the primary key itself is not causing any duplication of other columns because we don't have any other columns here. So by taking this design approach, we are avoiding duplication and keeping all the information in one place and then referencing them in other tables. So with this done, we are technically in compliant with the second normal form, but we can also do one minor refinement. If you notice, this course names are repeating. So just like how we did with the student table, we can create a separate course table that has a list of courses and their corresponding names, and course ID is the primary key. And then in the student course enrollment details, we keep track of student ID and then the course ID. So that way, if you need to correct the course name, all you have to do is come to this one place and update the course name. And in the student course table, we are referencing the course using an ID. So with this done, we now have a 3-table design. Instead of storing all the information in one table, we have split the information into 3 different tables: student, course, and student course table. And we are in fact compliant with second normal form rules. So with this done, let's move on to the next phase, which is the third normal form. So we are in third normal form now. Now our objective here is to eliminate redundancy caused by non-primary key columns. Now here are the rules for third normal form. The table needs to be already in second normal form. When you say your table is in third normal form, it is implied that your table is already in second normal form and in first normal form. So only then you can come to third normal form. And then we are interested in looking at duplication of data caused by dependencies between non-primary key columns. So there could be several other columns in your table, and there could be duplication caused because of these dependencies among non-primary key columns. Now these are also referred to as transitive dependencies. So let's take a look at an example of this. Now let's say we have student S05 Akil who recently joined the program, And it so happened that Akil is also from Dallas, Texas, and from this zip code, 75201. Now, if you look at Bob's information, Bob is also from Dallas, Texas, and same zip code. Now, these columns are all non-primary key columns, and somehow there is some repetition of data going on here. So every time a person joins with the same postal code, you're going to repeat the city and state information. So this is an example of transitive dependency, because from postal code, we can find the city, and from city, we can also find the state. Or we can simply say that from postal code, we can find a city, state. So that means these columns are functionally dependent on postal code. Like we discussed earlier, we can keep this postal code city state mapping in a separate lookup table and reference that in student table. So for example, it will look something like this if you decide to take that approach. So in student table, we store only the street and postal code. And we have a separate table called location, which has the mapping between postal code, city, and state. So here we are storing, if you look at this particular postal code, that is the primary key. We are storing the city and state information only once. By doing that, we are avoiding redundant storage of data for these two rows. We are technically in compliant with the third normal form now. However, we had to weigh the pros and cons. So we can keep breaking a table into smaller and smaller and smaller tables like this. But then that also increases the design complexity. Now, if you want to find the complete address, now you have to join two different tables. So sometimes this kind of complexity may not make sense. So you may want to consciously avoid doing this kind of separation. Instead, it might be a lot more useful if you just keep all the data in one place, and knowing that there might be some redundancy of data. So with that consideration, we can go back to our 3-table design. Instead of 4 tables, we can just leave it at 3 table. And then we are going to pretend that there is no functional dependency between city, state, and postal code. And then we can comply with third normal form now. Now, to summarize, we went through 3 stages of normalization, and we took care of basic table structure in first normal form, and then we eliminated redundancies caused due to composite primary keys. In fact, the first 2 phases, we did the bulk of the work, and in the third phase, the third normal form, we did not do much work. We tried to do some minor optimization, but that also was not so beneficial. So we just went back to the design we came up with, the second normal form. Now, these 2 stages are a common point of confusion for students and professionals alike. What exactly are we doing in second normal form and third normal form? So what I'm going to show is another solution that approaches the same problem in a slightly different way, so that I can emphasize the difference between second normal form and third normal form. So let's see how that solution would look like. So for this alternate solution, what we are going to do is we are going to revisit this second normal form and the third normal form stages. Now, if you look at the rules for second normal form, the table needs to be in first normal form, which we already comply with. And we need a primary key, and we also need to avoid duplication caused by composite primary keys. So we had this table structure after first normal form, and we elected to use student ID and course as the composite primary key columns. Now what we are going to do in this solution is that instead of using student ID and course as the primary key, we are going to introduce a new column called enrollment ID. So every time a student enrolls in a course, we are going to assign a unique number. So for example, E01 is for S01 joining math, and E02 is S01 enrolling in chemistry, and so forth. So every time a student enrolls in a course, We're going to add a new row, and we are going to assign a unique enrollment ID. So this is a made-up column, and this is also called as a surrogate key, because this data is it's not coming from any of these existing columns. We just made this up, and usually in databases, this will be an auto-generated column. So for example, even student ID, if you look at it, it is an auto-generated column. Every student is automatically assigned a unique student ID. Now, since we have a surrogate key now, an enrollment ID, we can use that as a primary key because each row gets a unique enrollment ID. So we have a unique enrollment ID for each of these rows. So that means it's a good candidate for a primary key. Now this primary key is not a composite primary key. It's a simple primary key because it's a single column primary key. So what this also means is that this design is now complying with the second normal form rules. Because if you look at it, second normal form rules say that the table needs to be in first normal form, and there has to be a primary key. And if you have a composite primary key, you need to avoid duplication. Since we don't have a composite primary key, we don't have a duplication issue caused by the primary key itself. However, we have non-primary key columns that are causing duplication of data. So all these columns are getting duplicated because of some other non-primary key columns. So that is what we are going to handle in third normal form now. So let's now apply third normal form rules. With third normal form, we are going to eliminate redundancies caused by other columns, dependencies among other columns. So with this structure, we have enrollment ID as the primary key, and then we have so many non-primary key columns. And we also know that there is a dependency between student ID and name and complete address. Every time a student ID repeats, the name and complete address is also repeating. Once again, the way we are going to handle it is to break this big table into smaller tables. So we're going to create a student table and use it as a lookup table from here. Even though we are optimizing the solution in the third phase now, the solution looks pretty much similar compared to the previous solution. So we now have a student table that has student information. Every student appears only once here. And then we also have a course table similar to the previous approach. So each course has a unique ID. And then in the student course table, we have enrollment ID as the primary key. And every time a student enrolls in a course, we are going to record the corresponding student ID and course ID. So this design now complies with the third normal form, and we are avoiding all the duplication caused by non-primary key columns. So with this done, we are once again coming up with a 3-table design that complies with the first 3 normal forms. And by doing this, we also came up with an efficient design where we can easily query student details from student table. And if student changes their address, we can come and update the information in one place. Similarly, if they change their name, we can come and update in one place. And if a student enrolls or withdraws from a particular course, we can record that information in a student course table. And then we also have a course table which has the course name, and we can also extend this to record instructor ID or semester information and so forth. So to summarize, we walked through 3 stages of normalization. So normalization is a simple process where we look into specific aspects of design in each of these stages. In the first phase, we looked at how to organize information properly in a table. So we looked at how the row should be, what the column should be, and so forth. And then in the second phase, we looked at eliminating redundancies caused by composite primary keys. And in the third phase, we looked at redundancies caused by non-primary key columns. Hope you found this session useful. Thank you for watching.